Hey everyone. So today we're going to talk about probably one of my favorite things in chemistry, which is everything, obviously. Significant figures. I know that this is frustrating to a lot of students. So what I try to do is, you know, um, make it as easy as possible for you guys to digest and kind of understand what significant figures are and also why they're actually important. So first off, we need to have a pretty decent understanding and working definition of precision and accuracy. It's up to us to understand that all of our measurements must be either precise or accurate, or some combination of both or neither. Precision oftentimes refers to a set of measurements, multiple measurements, and precision is going to specifically refer to how close a set of measurements are to each other. By looking at the bullseyes that are listed down below, the first two on the left-hand side are going to be measuring precisely, because the sets of measurements, the four dart throws that were thrown, are all very close to each other. Now, the way that this works in the real world is if I go ahead and measure a sample of um, gold. I always like using gold. If I have a pile of gold and I put it on a scale and it says it's 25 grams, and I take it off the scale and then move it back onto the scale and it says it's 25 grams, those two are the same measurement, and the set of measurements, trial one and trial two, are precise. Accuracy specifically refers to how close a measurement is to the true value. So, for example, if I kept weighing my gold and it kept saying 25 grams, and I was like, I was supposed to get paid 50 grams of gold, and I know that the sample is 50 grams, then the sample would be inaccurate. Now, one of the questions I always like to pose to my students is, which do I prefer, precision or accuracy? And most of the time, students go for accuracy, but actually, we want precise measurements. Oftentimes, if you have an inaccurate measurement, and it's consistently inaccurate, it usually means that your device is broken or not working. So, for example, with my gold, I kept weighing it. I knew that it was 50 grams, but the scale kept saying 25 grams. There was something wrong with my scale. Now, what does this actually do for us? What does this actually tell us? Well, when we go about measuring things, when we go about measuring the mass, the length, the volume of a substance, knowing how precise and accurate our glassware, our devices are, is important. And when we state a measurement, we need to be able to state how we measure that thing. How precisely we actually measure that thing, and that's what significant figures do for us. It basically tells us how good our measurement was. So, for example, here, if I were to go ahead and look at a beaker, let's go ahead and say that it measures 100 milliliters. And I know it measures 100 milliliters, but there was no markings on it. Fill it up about halfway, we'll say about right there. The best you could tell me is that I think it's maybe 50 milliliters, could be 50, 60, it could be 40, I don't know. Um, but if I had a better beaker, if I had a better measuring device, right? Here's my beaker over on the right-hand side. This one also measures 100 milliliters, but the big difference is that this one has graduations. This one has markings. So when I'm looking at something like this, I can say, oh, it was actually pretty close to 60. I know that it was maybe 57 milliliters or 58 milliliters, somewhere along the lines of that. So the measurement that I list, the measurement that I give, is only as good as the device that I use. So significant figures specifically tell us all of the known digits in the measurement plus the first unknown or estimated one. And without the actual device, the measuring device, it's hard to kind of remember that every number we see in chemistry technically is a measurement, and we must be considerate of these significant figures. So how do we actually go about identifying significant figures for a measurement? And there's a set of rules that we have. I think the most basic and straightforward rule is that anything that isn't a zero is significant. So if I were to go ahead and look at a number like 599 inches, 599 centimeters, there are three significant figures, 599. Now is where we kind of get into the funky rules for significant figures. It has everything to do with zeros and their placement against non-zero numbers. It has nothing to do with the decimal, and you'll see what I mean when I get there in a second. So the first type of zero that I have is a leading zero, and leading zeros are to the left of non-zero digits. Leading zeros are never significant. So some examples of this, I could have a very small number like 0.0034. Maybe I'm measuring seconds or inches, something like that, but a very, very small measurement. This only has two significant figures. And the reason that is because all of these zeros right here are to the left of the non-zero digits, are to the left of the 3 and the 4. That makes them leading zeros, and leading zeros are never significant. The second type of zero that we're going to be looking at are trapped zeros. And trapped zeros are essentially trapped by non-zero digits. Trapped zeros are always significant, and that kind of makes them different from leading zeros. Some examples of trapped zeros would be like 1005, and all four of these digits here, all four of these numbers are significant, and we know that this zero and this zero here are significant because they're in between the 1 and the 5. So essentially when we're looking at these numbers and trying to identify if a zero is significant, it's all about its placement compared to other numbers. Now, if you're following along, you're probably hoping and seeing that there's one more type of zero that we can have, and that's going to be a trailing zero. Trailing zeros are the ones to the right of non-zero digits. And this is where the decimal place comes into play. Now, as far as trailing zeros go, trailing zeros are only significant if there's a decimal point present. If the decimal point is not there, then the trailing zero is not significant. If the decimal point is literally written on the paper, then the trailing zero is. So for example, I could look at a number like 520. 520 has a trailing zero to the right of the 5 and the 2. Because there's not a decimal point, this number only has two significant figures. But by adding a decimal point, so saying that like, hey, I took the time to actually measure this zero, I know it's 520 pretty much on the money, that makes that zero significant. And all I have to do to indicate that is add a decimal point. The first 520, the one in part B, is saying it could be 520, it might be 510, it might be 530. We are not 100% certain on the tens place of the measurement. So let's go ahead and look at a few examples here just to make sure we're kind of keeping up with how to identify numbers of significant figures. We have 5,099 seconds. We know that our non-zero digits are significant, so the 5, the 9, and the 9. And this zero here is a trapped zero, making it significant. So there are going to be four significant figures here. The next number is 95.0 meters. 95, we know, are non-zero digits. They are significant. And we have this zero that is trailing. It is to the right of the non-zero digits. Trailing zeros are significant if there's a decimal present. And would you look at that? There's a decimal drawn right there. So it is. There are three significant figures. The next one is 0.0023 meters cubed. As far as this one, we go the 2 and 3 are significant. The zeros up front are leading zeros, and leading zeros are never significant. This one has two significant figures. Moving on, we have 9.020. The 9 and the 2 are significant, and the 0 in between the 9 and 2 is also significant because it's a trapped 0. The 0 at the end is a trailing 0, and it's significant because there's a decimal present. In terms of scientific notation, where we have this number written off to the right-hand side, we can just ignore that when we're trying to determine how many significant figures something has. This measurement has 4 significant figures. And the last crazy fun number that we have here is 1010101000 hertz. Kind of feels a little bit binary there. But let's go ahead and get started with it. So we know that the ones are significant, and we know that all of the zeros in between each one of the ones is significant as well because they are trapped zeros. The zeros to the right of the last one are trailing zeros. And remember, trailing zeros are only significant if a decimal is present. Since no decimal point has been drawn, those last 2 zeros are not significant. So this last number has 1, 2, 3, 4, 5, 6, 7 significant figures. Now, it might seem odd that we're literally counting how many significant figures there are present, but it's actually important for us to understand how many significant figures are present because when we do operations, for example, multiplication and division, or addition and subtraction, the amount of significant figures in our measurements can change. So let's go ahead and get started with the most basic type of operation that we are going to see, and also the most common, rather I should say, the most common type of operation that we'll see in chemistry, multiplication and division. The rule for multiplication and division significant figures is as follows. Your answer must have the same number of significant figures as the measurement with the least amount of significant figures. So let's go ahead and try this out. The first operation that I have here is 34.2 centimeters times 49.0 centimeters. What I always like to do is punch that number into my calculator and get a number. Now, if this was a math class, the answer 1,675.8 centimeters squared, would be perfectly fine. But because this is chemistry, we must change our final answer such that it represents how I actually took my measurements. Now, once again, the rule for multiplication and division is that my answer here has to have the same number of sig figs as the measurement with the least amount. By looking at it, it looks like 34.2 has 3 sig figs, and 49.0 also has 3 significant figures. So as far as this goes, my final answer must have 3 significant figures. Change my final answer, and the way I do so is by counting from the left to the right. So my answer has to have 1, 2, 3 significant figures, and I'm going to use the 5 here to help round the 7. It looks like my final answer is going to be 1,680 centimeters squared. So I'm going to go ahead and do this again with this calculation down below with division. Now, like I said, I always like to go ahead and type in the multiplication or division completely into my calculator and get a final answer. So I get 62.04 seconds squared divided by 0.08 seconds. And it looks like I get out of my calculator 775.5 seconds. Now, if I'm looking at my my number of significant figures in my measurements, over here I have 4 significant figures, and over here I only have 1. That means that I have to change my final answer such that it has 1 significant figure. 775.5 ends up rounding to 800 seconds. Now, something that students like to do when they do these calculations and change their final answers is they like to drop off zeros. One thing you should always make sure to check on is that your final answer is somewhat close, and by that I mean within the same order of magnitude as your original answer. 775 is in the same order of magnitude as 800, so 800 seconds is a perfectly fine final answer. The last type of operation that comes up in chemistry in terms of significant figures is addition and subtraction. This one isn't as common, but the rules are still important. When we're adding and subtracting, our answer must have the same certainty as the measurement with the least amount of certainty. Essentially, what this looks like is the answer, our final answer, is going to have the same number of decimal places as the measurement with the least. So once again, we have some examples. I always like to, once again, plug everything in exactly as it's written to get some sort of answer. So we have 83.25 plus 92.4 gets us 175.65 seconds. But we know that this final answer must change. I see here that my second measurement goes to the 10th place, while my first measurement goes to the 100th place. The least certain measurement goes to the 10th place. That means I must round to the 10th place. My final answer is going to be 175.7 seconds. For my last calculation here, I'm going to punch it into my calculator. 95,000 meters subtracted by 2,400 meters to go ahead and get 92,600 meters. Now, as far as this goes, I must identify the certainty of each one of these measurements. The first measurement is certain to the thousands place, while the second measurement is certain to the hundreds place. The thousands place is less certain than the hundreds place, so I must round there. My final answer ends up being 93,000 meters. Once again, thanks so much for watching. And if you guys have any questions, feel free to shoot me an email. Thanks a lot.